Airplanes are beautiful dreams. Engineers turn dreams into reality. Hayao Miyazaki from The Wind Rises. I was probably about 10 years old when I first discovered the B-29, and I saw beauty. A polished aluminum exterior, sleek form, and stepless cockpit. I still think it may be the best looking aircraft ever built. Regarding dreams though, a nightmare is also a type of dream. First, I need to talk about what the B-29 did. I don't want to include this section, but I also don't want to be taken out of context. Let's start with Japan. The atrocities committed by the Imperial Japanese Army in China, Korea, and much of Southeast Asia through the 1930s and 1940s represent the absolute nadir of humanity. I believe they may collectively represent the single worst atrocity in modern history, and these actions cannot be forgiven. These atrocities only ceased when Japan's surrender was forced by the Allies in August of 1945. And that was achieved by bombing 67 of Japan's major cities. Bombing is an understatement. The most destructive was the firebombing of Tokyo. In a single night in March of 1945, 16 square miles of Tokyo was turned to ash. And I mean ash. There was nothing left. Here is a 16 square mile circle overlaid over Manhattan for context. This level of indiscriminate destruction was repeated over dozens of other major civilian centres. I will not give my opinion on whether this was justified, moral, or necessary. You need to come to your own conclusions on that matter. But the comment section of a video about the B-29 turret system is not the place to discuss this. And if you feel you can sum up your thoughts in a sentence, I'd suggest you go and read or listen to some of the sources I've posted in the description. I'm not here to try and give a balanced view on the ethics of city bombing, and I can't undo the sanitised view much of the world was given about the Pacific Campaign. Most importantly, I want to make clear that the bombing of cities was and is awful. You can believe it was entirely justified and necessary and prevented further tragedy, but at the same time you can be disgusted by it. Alternatively, you may believe it was entirely unwarranted, but equally be unable to provide an alternative. None of this should take away from the sacrifices made by the aircrew who were forced to carry out this awful campaign, the Allied foot soldiers who fought and died in a vicious offensive, and the young Japanese soldiers whose lives were wasted thanks to a bastardized interpretation of Japanese traditions passed on to them by an emperor who fancied himself a god. Now, I think there's one small thing I'm missing. Almost every discussion on the bombing of Japan is overshadowed and devolves into the atomic bombs. These, of course, carry their own moral issues, but ultimately they constituted a minority fraction of the most destructive urban bombing campaign of all time. Remember Hiroshima and Nagasaki, but don't forget the other 65 cities. In summary, the only opinion I'll give you on the matter is this: the bombing of civilians should never be celebrated. The technology we'll look at today played a part in that, and I included this disclaimer to make absolutely clear that although that technology was fascinating, I do not want to be seen as glorifying what it was ultimately used in aid of. Well, I always said to myself I'd never do a video on anything from World War II. There are already enough guys on YouTube making excellent videos on that topic. But a viewer suggested this to me, and honestly it's far too interesting to pass up on. And it looks like no one else has done an in-depth video on it yet, so I decided to make an exception. Besides, many of my videos are done about historic computers, and today we'll be focusing on another historic computer. Except the fire control computers in the B-29 were mechanical and analog. Let's make sure we agree on exactly what that means. Mechanical analog computer. Let's start from the end and work backwards. Okay, so computer. In my ideal world, a computer would be exclusively anything which is Turing complete, or at least Turing complete in principle. Now, I'm not getting into what that means now. I'll discuss it more in the future. But anything that's Turing complete can do anything that any other Turing complete device can. As I've said before, this is sort of where the "can it run Doom" thing comes from. If we were somehow able to give the B-29 fire control computer memory and an arbitrary amount of time, it could not run Doom. It was not Turing complete. Turing completeness does not even make sense in the context of this machine. The word computer is more of a linguistic term in this context. It loosely means something that can find or approximate a solution to a family of mathematical functions. Back in the 1940s, a computer was either a person or something that resembled the B-29 fire control computer. Anyway, now on to analog. The device you're watching this on is a digital electronic computer. I don't think anyone is going to disagree with that. Digital because it operates on discrete values, or voltages. And electronic because it, performs that digital logic using electricity. Analog electrical computers are also possible. I'll be honest, I know very little about them. But they use a continuous range of voltages for computation. No two analog devices are the same, but barring failed components, two digital devices will always give the exact same result. A really, really common misconception is that vacuum tube computers were analog. They were not. They were digital. A vacuum triode acts essentially identically to a transistor, and when used to build logic gates, they were fully digital. But even a vacuum tube computer didn't exist when the B-29 fire control computer first flew in 1943. The B-29 computer was a different beast entirely. The system as a whole had a few vacuum tubes, but they were not used for computation. We'll get to them later. The computer itself was electromechanical. That means it consisted of gears, clutches, and other various moving parts, all driven by electrical motors. And just to round off our picture, though the B-29 computer was analog, mechanical computers can be, and have been, digital. There even exists a design, to some extent, of a Turing complete digital mechanical computer. But we are definitely not getting into that now. In fact, like most prior US World War II bombers, the B-29 already had an analog computer. It was the Norden bomb sight, designed to drop a bomb into a pickle barrel, which it could probably do on a perfectly clear day, with no flak, or fighters, and no turbulence, or stratified wind, and perfect airspeed and altitude data, and perfect aero. The Norden bomb sight was not a good solution. The mythos surrounding it may have cost quite literally hundreds of thousands of civilians their lives, and indeed tens of thousands of aircrew, and it is yet another story we will not be going into now. I would like to argue that the B-29 fire control computer was not perfect, but it was no Norden bomb sight. Now, a topic like this requires special care and attention. So, the tools I use to explain the B-29 fire control system will be a little different from what I normally use for video explanations. I'd be happy to bet a significant proportion of my viewers know how a differential works due to this video, or they know how to lead a target as a B-17 waist gunner, or even how best to fly to avoid flak. Some of the informational films produced around the time of World War II were absolutely fantastic, so I've decided to use them as inspiration for this video. As an aside, I suspect many of them were terrible, but just the good ones have survived and made it onto YouTube. Hey, look, survivorship bias. I'm sure that won't come up again in a video about World War II bombers. Anyway, I've constructed some reproduction parts from the B-29 system using my tiny model-making lathe and my 3D printer. Hopefully, these will help viewers build up a picture of the computer's operation. My parts are not like-for-like replicas, they're simplified and modified to aid explanation. But I will show schematics of the actual parts from the B-29 computer alongside. This is also the first video I've made where I've done a proper field trip as such. The history of this channel has been me making a video about something and then stumbling upon a real-life example of it just a few weeks later without even knowing it was there, or just not being able to make it there before releasing a video. Well, this time I visited the only B-29 in the UK. The American Air Museum, which is a part of the Imperial War Museum in Duxford, has one. It was really fantastic to see in person. I've loved this aircraft since I was a kid. And the story of how it got there was incredible too, but that is definitely a story for another time. I got plenty of footage and photos of it on my old film camera, so they'll be appearing where relevant. My footage isn't brilliant, the lighting wasn't great there, but it'll do. The museum contains many wonderful examples of some of my favourite aircraft of all time and some of the best looking aircraft of all time. They also have an A-10 Warthog because, I guess nowhere can be perfect. Some of the aircraft I filmed are relevant to this story, some are not. I'll occasionally include footage of them on screen along with my one-sentence reviews. The US's most produced heavy bomber of World War II was the B-24 Liberator. Everyone remembers the B-17, but it was the B-24. My grandfather was stationed in Kent during the war, and he always spoke of Liberators, but for some reason, the B-17 is the one that became the symbol of American city bombing in Europe. Of course, the British equivalent was the Lancaster. Now, the problem with all these aircraft was, well, none of them were really very good. I'll let Lord Hardthrasher explain in more detail at the link here, but the B-17 is just the example he runs with. It was slow, outdated, and carried a frankly pathetic bomb load, just 4,000 pounds on a typical assignment. The proposed solution for the B-17 was to pack it full of as many guns as reasonably, and sometimes unreasonably possible. And the result of that was turrets that increased air drag and added even more mass, reducing the cruising speed further. Each turret was manned by a crew member who was exposed to the far below zero temperatures at altitude and had to contend with the noise and recoil from the guns. And let's not even get started on the waist gunners. Does this look like an easy method of shooting down a fighter to you? Now, of course, that shouldn't take away from the fact that these men still scored an unbelievable amount of kills. The ball turret, though infamous, was particularly well built and effective. But even with all that armament, without the fighter escorts that came later in the war, Allied bomber groups were not far from being sitting ducks for the Luftwaffe and for ground-based flak. Some viewers will point out the notorious ruggedness of the B-17, but let's go find some Luftwaffe gun footage. All that took was a split-second burst of 20mm cannon fire from the front or the rear of the aircraft, and it'd essentially be raked. No armour could protect a crew from that. And put away that survivor bias infographic now, it's not relevant, yet. Viewing actual footage, when flown without fighter escorts, these so-called fortresses suddenly appear horrifyingly vulnerable. and honestly, the B-24 or even the Lancaster were not much better. The end result was utterly unacceptable losses to Allied aircrew. About 50% of RAF Bomber Command were KIA. But Britain did build an aircraft with a good track record of hitting German targets while sustaining much lower losses once they figured out how to use it properly. For most of the war, it was almost invulnerable to both fighters and flak, as it flew too high and too fast for both. The Mosquito, hands down my favourite British aircraft of World War II. The main problem with the Mosquito was it was small, or put alternatively, we didn't build enough of them. So instead of building more, how about a large aircraft that could fly high and fast? In a sense, that was the B-29. So let's take a look inside the B-29. Most of the crew were housed in 2 pressurised compartments connected by a tunnel. The pilots, bombardier, navigator, radio operator and engineer all normally sat in this forward compartment. The communications tunnel passed over the unpressurised bomb bay. By World War II standards, this was enormous, capable of carrying a 20,000-pound bomb load for 1,500 miles, with enough fuel for the return trip. That is about double the bomb load and range of a Lancaster. Right, stop there a second. Normally when I spot mistakes like this, I edit them out and you never hear about them, but I just parroted something that's really commonly mentioned online there, so I want to correct it. The B-29 could absolutely carry 20,000 pounds in bombs. It just couldn't carry them all the way from the Marianas to Japan. Early on in the campaign, a typical bomb load would be something like 5,000 pounds, so similar to the B-17, but more than double the distance. The fact that it could drop any bombs at all on Japan from the Marianas was incredibly impressive for the day. As 1945 progressed, loadouts were altered. The bombers were flown at different altitudes, and 10,000 pounds seems to be a more representative figure. It varied heavily. Some raids carried up to 15,000 pounds of bombs. That did require stripping out equipment. We'll discuss that in a later chapter. The fire control station was in the rear pressurised compartment. Here, the top gunner sat on a rotating chair with outside visibility provided via a bubble window. The left and right gunners sat at either side of the compartment at their own bubble windows. The rear of this compartment is shown occupied by bunks in my model, but most of the flown B-29s replaced this area with seating and instrumentation for an electronic countermeasures operator and for the radar operator. The B-29 had a powerful ground scanning radar and could therefore identify targets without direct visual contact, but that is not a story for today. Finally, at the rear of the aircraft, a final small pressurised compartment housed the tail gunner. The tail guns were also part of the fire control system. By the late war, even a high-altitude and fast bomber could theoretically be intercepted, so the B-29 would need a capable suite of defensive armament if it was to fly unescorted. And that is how Boeing arrived at the remote-controlled turret solution. Seating the gunner away from the turret allowed the profile to be lower, thus reducing drag, along with the multiple benefits of housing the crew in a heated, pressurised compartment. It could engage enemy fighters effectively from 900 yards, as opposed to an optimistic estimate of 600 yards for a Japanese fighter. That's about 2 seconds where a crew could fire on an attacking aircraft before it could open fire on them. Some smaller late war aircraft also exhibited single remote turrets, but none were anything like as complex or effective as those on the B-29. Let's discuss how the turret system worked as a whole. There were 4 rotating turrets, each able to rotate 360 degrees and pitch anywhere between the horizontal and the vertical. Now, I don't know much about guns, but I know what that block with a tube is. Each turret housed 2 Browning 50 cal machine guns. The upper front turret often housed 4 guns. As I mentioned, the tail turret was also connected to the central system, providing an additional 2 50 cals and a 20mm autocannon on some variants. These turrets were controlled by the 5 sighting stations. The bombardier doubled as the nose gunner, using a sight mounted on a pivot arm at the very front of the aircraft. 2 identical pedestal sighting stations were installed in the blister windows in the gunner's compartment. The upper blister window housed an additional sight that differed from the others. This was a ring-type sight, able to rotate freely on a ring below the window. As the upper gunner rotated on his barber's chair, he'd rotate the sight with him, giving full 360-degree coverage around the aircraft. The final sight was a pedestal sight installed in the tail gunner's compartment, with the tail gunner sat behind a protective armoured plate and armoured glass. 5 turrets and 5 sights, so 1 per gunner? Absolutely not. The whole system was, in a sense, networked together, with gunners able to take control of additional turrets as required. Every sighting station came with a switch box. The nose gunner could take control of either of the forward turrets. For example, here, he'd select the lower turret using the switch box but release control of the upper forward turret. The upper gunner would generally have control of the upper rear turret. However, with the forward upper turret released, he could also take secondary control of that using his selector switch. The nose gunner in this case would take priority though, as he was able to take back control at any time of that turret. The side gunners shared primary control of the rear lower turret, and could pass control of it to one another with a dedicated switch box in the middle of the cabin. They were also able to take secondary control of the tail turret or the lower nose turret. Of course, the tail turret was primarily in control of the tail gunner. However, if he became incapacitated, the side gunners could assume control of it. And that included the 20mm cannon where fitted. I've only walked through a few possible control configurations there, but the advantages are clear. The loss of a gunner did not mean the loss of a turret, with other crew members able to immediately gain control. In fact, every sighting station was fitted with a dead man switch. If a gunner let go of the sighting station, any turrets he was controlling were released to the rest of the crew. The ability to pass over and take control of multiple turrets gave single crew members the ability to put a lot of lead towards a target if necessary. Rather than a waist gunner on a B-17 having a perfect line of sight to a target but only a single 50 cal, a waist gunner on a B-29 could potentially bring 6 50 cal guns to bear at once. As for how this was possible, we need to build up our diagram a little further. I'm just going to show how the turrets were controlled in azimuth for now, but this whole system was replicated for elevation too. Let's learn about Celsins, also known as synchro motors. Back in 1943, they were called Celsins, so that's what I'll call them in this video. It's short for self-synchronous motor. A Celsin is essentially 2 specially constructed motors wired together such that turning the shaft on one causes the shaft on the other to rotate by the exact same amount. I was going to buy a couple to show off here, but they generally require 3-phase high voltage, and I'm not going to get into all of that now. So instead, here are a couple of servos replicating the effect. Check out Curious Mark's video linked above for more details. Now, I think we can all see why this would be incredibly useful to drive a turret, but there's a problem. Celsins output a minuscule torque. They're primarily used in aviation to turn dials on instruments, not spin heavy turrets around at high speed. The minuscule torque is because they only output a minuscule current, so it sounds like we need an amplifier. In the B-29, the receiver Celsin on the turret was connected to an amplifier. This is referred to as a servo amplifier. There was one servo amplifier for each turret, and each used vacuum tubes to amplify the small current from the Celsin. Incidentally, these units are probably the reason the fire control computers, which we'll get to soon, are often misattributed as vacuum tube computers. Vacuum tubes were present in the computers, but they were only used for signal amplification. They were not used for computation. The high current output of the servo amplifiers was used to drive a generator, which provided stable DC current to the drive motors on the turret, allowing it to be rotated at high torque. When the turret came into alignment with the sight, the current passed from the input to the output Celsin would drop to 0, meaning no current was amplified and sent to the generator, meaning the turret would stop moving. And that closes the control loop for the turret. Now, this in itself would be a highly advanced system for the time, but there's a glaring issue apparent. Let's have a look at the system I described and just consider the forward upper turret. The turret points where the gunner points his sight. So yeah, that is not going to work. Clearly a correction is needed for parallax. That's the distance between the turret and the sight. And that's not as easy as I make out here. Consider a fighter approaching from an oblique angle. And additionally consider that the gunner could take control of a second turret that was positioned a different distance away from the primary. And now consider the speed of the B-29 relative to the exterior airflow. Air resistance is going to introduce a curve to the bullet from the perspective of the gunner. In fact, here's a formula for air drag on a bullet. But that also varies with altitude and temperature. So we're going to have to take those into account too if we want to actually hit anything. That means pointing the gun somewhere upwind of the target. And of course the degree of upwind lead is going to vary with distance to the target. Next is bullet drop. Again, this varies non-linearly with distance to the target. We need the gun slightly high in elevation compared to the gunner's aiming point. And finally is the correction that appears impossible at first glance using 1940s technology: lead. Unless an enemy approaches us directly, their aircraft will have moved relative to us in azimuth, and indeed in elevation, in the time it takes our bullets to reach them. So we need to somehow account for the relative velocity of the two aircraft and point the guns somewhere ahead of the enemy aircraft. Since World War I, naval vessels were able to apply similar corrections to their guns using huge mechanical computers. These would take inputs such as range and relative velocity from the rangefinder and automatically adjust the gun's azimuth and elevation. By World War II, fire control computers were widely used in ground-based anti-aircraft cannons, but shrinking one down for use in an aircraft was an entirely new and daunting task. But there was no single technology in the B-29 fire control system that I would describe as new for the 1940s. It was just the first system of its type to combine and miniaturize existing technologies into something compact enough to fit into an aircraft. The B-29 didn't have one miniaturized fire control computer. It had 5, one for each sighting station. We'll spend the next few chapters learning how they worked. I want to start with lead correction, because even though it looks like magic at first glance, it's probably the easiest to explain. Lead computing gun sights already existed for a couple of years prior to the B-29, but the B-29's fire control system had a particularly well-implemented example. First, let's have a look at the sight itself. Looking through the sight glass, the gunner would see a circular arrangement of dots projected onto an inclined glass screen. To effectively target an enemy, he was required to first dial in the wingspan of the fighter using a wingspan dial. Gunners would memorize the wingspan of Japanese fighters. He'd then place the central dot on the fighter and track it. The distance wheel in his right hand required constant adjustment to keep that fighter framed. This wheel adjusted the diameter of the circular dots, and the objective was to constantly frame the wingspan of the fighter within this circle. This is how distance to the target was provided to the computer. Provided the gunner could keep that fighter framed in the reticle, he was practically guaranteed to hit it when his left hand depressed the fire button. So first, let's explain how that reticle was created. Here's a plot of apparent size of a target with distance to target. The apparent size, or the size in the viewfinder, is proportional to the wingspan divided by the distance. As wingspan increases, the graph is stretched in the y-axis, as shown. Okay, let's take the plot for a given wingspan and inscribe it onto a circular gear such that it forms a slot through the gear. In fact, let's do that multiple times in a circular pattern around the gear. This gear was connected to the distance input wheel as shown. As the gunner adjusted the distance wheel, this slotted gear would turn. Okay, now let's add a second gear with a mirror image of the same pattern and shine a light through the assembly. We see that circular dot pattern. Keeping the second gear still but adjusting the distance wheel adjusts the diameter of the pattern. But that second wheel was connected to the wingspan adjustment dial. Just visually, you can convince yourself that the aggregate effect of adjusting that wheel was the same as stretching the graph I just showed. So excellent, we're almost there. But a third gear was added between them. This prevented adjacent legs of the pattern interfering with one another, and it also made the projected dots appear cleaner. The wheel was turned proportionally to the other two to always ensure it allowed light to pass through. That was done using a differential. There were a lot of differentials in this computer. The light that passed through these three wheels was reflected upwards by a mirror and again into the gunner's eye line using an inclined plane of glass. And the combined outputs of the span and distance gears were fed into Celsins to be passed into the computer as the distance to target input. So now we have a working sight. You could even call it a rudimentary head-up display if you wanted. Let's find out how the rest of the sighting station worked with the computer to calculate lead correction. Here I have an electrical motor connected to a circular weight. If I spin up the motor, this forms a gyroscope. I've mounted it in a frame on bearings so it's restricted to only pivoting in this axis. Each sighting unit on the B-29 contained two similar gyroscopes mounted perpendicularly, one in elevation and one for azimuth. Again, let's just consider azimuth. If I take my entire assembly and rotate it in this axis, what do you think will happen? Well, if you're unfamiliar with gyroscopes, that was unexpected. There are a few ways of conceptualizing why it does that, but the best explanation I've ever seen comes from the book Achieving Accuracy, which I mentioned a few videos back. Here's that explanation on screen. Feel free to pause or go through it, or just accept that gyros do that, like I did for about 20 years before I found that page. Okay, well, I'm sure we can all now guess how this would be useful. The faster we rotate the assembly, the faster the gyro processes. Let's add a micro switch below it. Now, if the gyro goes off axis, this switch will be closed. There were two such switches in the actual system, one for upwards and one for downwards deflection. Perhaps surprisingly, these two switches were the only lead outputs from the sight to the computer. So how did it know how much lead to apply based off of these binary inputs? The switch was connected to a DC motor in the computer. As long as the switch closed, the motor would turn. The motor output shaft was connected to a mechanical apparatus known as the axis converter. We'll revisit this in more detail later, but for now it suffices to know that the axis converter was simply a device which converted circular motion to linear motion. An output arm of the axis converter would slide the input of a potentiometer, which controlled the amount of current flowing into a coil. And that coil was situated next to a permanent magnet on the back of the gyro motor. As the potentiometer was driven forward, more current would flow into the coil until it generated enough magnetic field to pull the gyro back into its neutral position, closing the switch and stopping the motor from running. It should also be noted an additional variable resistor was connected to the range input wheel on the sight, and this provided the range input for the lead calculation. Now, we will be revisiting this circuit later, so if you don't fully understand it, don't worry too much about it. The important thing to know is that the current required to restore the gyro to its neutral position was proportional to the amount of lead to apply to the guns. But how was this actually output to them? That DC motor didn't just drive the potentiometer, it also drove a Celsin input. The more the motor turned, the more that Celsin would also turn and send the corrections to the output Celsin on the turret, applying the lead correction in the required axis. The way I've just described all that was really just for a single moment in time. Remember, the gunner would be continually moving the sight and continually deflecting that gyro, and therefore continually allowing the computer to apply lead corrections in real time. One of the difficulties with analog computers is there is no standardized building block. Unlike a digital computer, where building a single type of logic gate allows you to build anything, one arrangement of gears and wheels is unlikely to be useful anywhere else. And so we move on to the parallax unit, which shared basically nothing in common with the lead unit apart from its inputs. It took in the elevation, azimuth and range supplied by the gun sight in the form of shaft rotations from Selson motors and was able to compute the parallax corrections to be applied. I wanted to machine this on my lathe, but my little model-making lathe is just not equipped for making bevel gears, so I'm afraid we're still going to be stuck with the 3D printed models again. But before we do that, let's quickly figure out what we're trying to calculate. As the guns rotate in azimuth, the necessary parallax varies sinusoidally. That is, the maximum parallax is required when aiming at a target that is side-on to the bomber. No correction is required for head-on targets. For the full 360-degree range, this gives us a full cycle on a sine wave. For elevation, and yes, the computer computed parallax in elevation too, I kept that quiet earlier, only a quarter cycle is required. Maximum correction is applied when elevation is 0, and no correction when the guns are pointed straight up or down. And this varies with distance to the target. As the range increases, our sine waves are squashed on the y-axis. Okay, let's do azimuth first. The azimuth of the sight was passed into this gear, which rotated 4 times for a full rotation in azimuth. In other words, it rotated at 4 times the rate the gunner moved his sight in the azimuth axis. That gear drove this bevel gear, which rotated this main gear. The ratio between the pinion gear and the main gear resulted in a 4-to-1 step down, meaning this gear rotated at the same rate the gun sight rotated in azimuth. An eccentric pin here slid a bar back and forth, so a full rotation of the input caused the bar to be displaced relative to the sine of the gun sight azimuth. This is exactly what we're looking for. The movement of this ball on the end of the bar is relative to the amount of azimuth parallax correction that must be applied to the guns. Let's put that ball in a free housing and attach a rod below. And let's attach a pivot to that rod. This assembly is referred to as a waggle rod. The position of the lower end of the rod is proportional to the necessary parallax correction in azimuth. But what about range? This setup would only work at a given single range. We make the pivot point free moving and feed a threaded rod through this nut. Rotating the rod moved the pivot point up and down, and the rod was attached to the range input, which is also provided by the gun sight as discussed earlier. A Selson motor was used to drive a motor which drove the input gear, providing range. So as range to target changed, so did the pivot point on the waggle stick. This proportionally amplified or reduced the movement from the bar, meaning the lower end of the waggle rod moved proportionally to the necessary parallax correction in azimuth. Now, this would be great if we were only accounting for azimuth, but elevation correction also required computation. So the yoke here was actually free to rotate, and it was connected to the elevation output from the gun sight. Unlike the azimuth inputs, this gear rotated at the same rate as the gun sight elevation. So a 90-degree elevation would rotate the entire assembly like this. Now, the central gear rotating caused the waggle stick to move side to side, and side-to-side deflection of the base of the waggle stick could be interpreted as parallax corrections for elevation. But we have a problem. We've just removed our azimuth correction. So the elevation output was also connected to the first input gear here, but in reverse. This would have been via a differential. Any rotation of the sight in elevation would rotate this gear in the opposite direction of the azimuth inputs, but it would only do so at 1/4 the rate of the azimuth inputs. As shown here, this cancelled out the effect and ensured both corrections were output by the waggle stick. Azimuth on this axis and elevation on this axis. We'll come back to exactly what the waggle stick fed into soon. And for the final kicker, with the exception of the tailgunner's computer, all the computers on the B-29 had 2 parallax units. Remember, gunners could take control of 2 guns at a time, so that means duplicating this entire assembly for the second turret and adding it to the correction separately. Correcting for wind resistance only requires adjustments in the azimuth axis, and gravity drop only requires corrections in the elevation axis, so both were handled by a single unit, the Ballistic Correction unit. This was very similar to the Parallax unit, and for that reason I'm not going to describe it in detail here. However, it did take inputs from a separate unit that we haven't discussed yet, the Altitude and Airspeed handset. This was located at the navigator's station and allowed the navigator to dial in the necessary values, preferably well in advance of encountering any enemy fighters. As high precision was not required on these inputs, they were passed into the computer as relative currents determined by potentiometers within the unit. You'd think this unit would be pretty simple, but it actually pre-computed the correction factors for temperature, altitude and airspeed, so it looked like this inside. I'm not going to dissect this unit as I can't do everything in this video, but I think this emphasises that the fire control system as a whole was really the computer, not just those 5 individual boxes that were named the computers. So, these inputs were fed into the ballistic unit, which output azimuth and elevation corrections to a waggle stick, just as the parallax unit did. So now let's begin to understand how these corrections were made into something useful. After all, at this point they consisted of XY deflections of waggle sticks, not particularly useful on their own. One of the central units of the computer was the pantograph. The waggle stick from the parallax unit was attached here, and that from the ballistic unit here. This leg was left free, and this one therefore would move relative to the sum of the ballistic and parallax corrections in both the azimuth and elevation axes. So now we've computed all the individual corrections necessary to hit our target. It's time to put everything together. My videos typically start off quite general. Then they have a few chapters that are a bit more in depth. But there's usually one chapter, about 2/3 of the way through, that is really difficult to follow on first viewing. This is that chapter. Being able to see how each individual unit generated corrections by physically moving things is what many would describe as beauty in engineering. Putting those corrections together is far less visually appealing, and much more difficult to explain. Let's draw out what we have. We have azimuth and elevation lead outputs from the site. Both of these are fed into the computer in the form of rotations of Selson motors. That lead correction motor drove the output Selson, which provided the final azimuth for the turret. Then we have combined corrections for wind, gravity drop and parallax. These are already combined together via the pantograph to give a separate elevation and azimuth correction. So that gives us 4 inputs. In fact, you know what? Let's just consider azimuth. Everything I'm about to say applies to elevation too. We'll call our 2 inputs the sight input and the pantograph input. So, now we have the lead corrected azimuth and the ballistic corrected azimuth. Just add them together, right? Well, obviously wrong. I was obviously going to say wrong at that point, wasn't I? There are 2 issues with this. Number 1, we don't know the current azimuth of the guns, so if anything drifts or goes slightly out of alignment, the system would have no way of knowing where the guns are actually pointing. Number 2, the sight lead corrections are relative to the position of the sight. The pantograph corrections are relative to the current position of the guns, so we can't just add them together. To begin to solve these problems, let's add an azimuth follow-up. This records the current azimuth of the guns and passes it back into the computer via, you guessed it, Selson generators. This completes the feedback loop hinted at earlier and is why the system as a whole is referred to as a servo. So let's make use of that feedback. First, we need to make sure we can add our 2 correction types. Recall that ballistic corrections are relative to a different axis to lead corrections. What we need is an axis converter. So here it is. I won't go into detail on exactly how this unit works. It's essentially a differential but with some extra steps. But for the purpose of this video, it suffices to accept it takes in the current gun azimuth and the sight input and converts the azimuth angle to be relative to the current gun position. So that is both of our inputs now on the same axis. So we just need to add them and communicate the correction to the turrets. That sounds easy, but we also need to communicate back to the computer that the corrections have actually been applied. That's another feedback loop. First, let's take a look at the final component in the loop, the potentiometer resolver. This consisted of two pairs of potentiometers arranged like this. The bottom pair were connected to the output from the axis converter. The top pair were connected to the output from the pantograph. Either of the input arms could move any of the sliders as shown here. The bottom pair of potentiometers were connected to a motor which fed its output back into the axis converter, with the circuitry arranged such that the position of the bottom potentiometers mirrored the top pair. Does that sound familiar? It's the lead circuit from earlier. That azimuth follow-up motor drove the output selsin which provided the final azimuth for the turret. So, movement from the pantograph in the azimuth axis would trigger the follow-up motor, moving the lower half of the resolver, whilst outputting an azimuth movement to the turret. And movement of the lower half from the sight also triggers the motor until the potentiometer outputs a required voltage which is only achieved once the axis converter has moved the bottom half by a proportional amount, thereby adjusting the potentiometer. So the absolute position of the lower half of the resolver plus the relative position of the upper and lower halves is proportional to the necessary azimuth correction. As these two positions are physically added together by moving the contact point on the sliding potentiometer, that means the output voltage is proportional to the necessary correction. Because unlike in the simplified diagram I took from the B-29 manual, the two potentiometers are actually wired like this. That voltage is the final voltage applied to the gyro coil, which increases until the gyro switch opens, which stops the azimuth correction motor because the necessary correction has been applied to the guns for that moment in time. And that's it. We have a final output to the turret selsin and a closed loop which ensures the turret will always chase the desired position. Needless to say, I had to simplify things a little there and make some omissions. I didn't go into the circuitry for the time of flight network, which also alters the voltage to the gyro coils, ensuring the gunner is able to keep the dot on target after ballistic corrections are applied. And I didn't describe the input and output units which convert between current and shaft rotations to feed into and out of the computer. And of course I didn't explain how most of the computers had to incorporate corrections from a second parallax unit. For the full picture, you can look at the documents included in my list of sources. There are a few other features of the B-29 fire control system that I wanted to go into detail on. The original technical manuals have some really nice illustrations and explanations that I'm keen to share. Did I mention the original manuals are some of the best I've ever read? The first question you may be asking was, how did the gunners not accidentally shoot their own aircraft? The solution was already commonplace at the start of the war. A cam in a fire interrupter mechanism traced the outline of the aircraft and interrupted the fire of the guns if the sightline crossed the aircraft. Nothing special there. What was special was the fact that each gun in a turret was interrupted separately. The system was so finely calibrated that an obstructed gun could be stopped while a clear gun was still firing on the same turret. They were only about a foot apart. Interrupting the guns individually really feels like Boeing was showing off at that point, which they probably felt the need to do given the cost of the B-29 project. If I was the gunner with his head in this dome, I would be making sure to keep an excellent relationship with the mechanic that calibrated that unit. Onto armour. We all know the story. Armour is heavy, aircraft can't carry much, so where do you put it? Here is where the armour was located on the B-29. Priority on protecting the crew, though note how vulnerable the pilots and bombardier were to head-on attacks. The Japanese were more than aware and modified their tactics to use head-on attacks where possible. Now, the Japanese were outstanding aircraft designers, but by 1944 they were basically done. All their experienced pilots were dead. Their pilot training was absolutely atrocious, and the manufacturing standards for new fighters were inconsistent at best. The only aircraft built in numbers that could reliably intercept a B-29 were the Ki-84 and the Ki-45. Even for a once-in-a-blue-moon event of a well-built Ki-84 with a good pilot and well-refined fuel, only a single pass at a formation at altitude when attacking head-on was probably possible. They just didn't have the performance to come back around and overtake for a second pass. And we'll talk a little about low-altitude interceptions in the next chapter. Anyway, one element that was not vulnerable was the computers. They were enclosed in 3/8 of an inch hardened steel. Clearly, they were deemed important enough to warrant that extra mass. You know, it's just occurred to me, I've never discussed the form factor of these computers in this video. Okay, so as you can see here, they each took the form of a cuboid about 20 by 20 by 8 inches, so not really very big. And each weighed about 50 pounds. The dual parallax computers had a kind of protrusion on the back, a smaller box about 8 inches in size. So that was about 250 pounds for all 5 computers, plus the servo amplifiers, the amplodines, everything else. I imagine you wouldn't get much change from about £1,000, let's say. Not sure whether that overall would make a heavier or lighter system than something like on the B-17 or B-24. I suspect it'd probably be slightly lighter, to be honest. I know that the Sperry Ball turret weighed about a ton, including all the hydraulics. But surely these complex mechanical computers failed regularly. I can't find reliable data on failure rates, but as we'll see in the next chapter, it's a pretty strong assumption that they were at least reasonably reliable, despite what some people may have you believe. However, if one did fail or get shot up, it didn't disable the turret and it didn't stop the gunners from using that turret. Each sighting station was equipped with a bypass switch. This would give the gunner direct control of the turret, and they would have to estimate corrections manually, just like those B-17 waist gunners, except in a heated cabin and away from the noise and recoil. And speaking of the cabin, apparently it'd be intentionally depressurized with the crew breathing oxygen through masks if they encountered enemy fighters. I've seen a few videos that appear to contradict this, though those videos may well be propaganda newsreels. And again, as we'll see in the next chapter, just because something happens sometimes does not mean it happened all the time. Apparently, it's quite well known that the B-29 cockpit and turret system was an inspiration for the aluminum Falcon. I wouldn't know, I'm not a Star Trek fan. Regardless, depressurizing before spraying bullets around is more akin to my favourite sci-fi series, The Expanse. Anyway, as for the footage I could find, every turret had a camera installed which triggered automatically as the trigger was held and would run for a few seconds after. This gun camera footage was used to verify enemy fighter kills and is the reason that we can be reasonably confident in the numbers that I'm going to present in the next chapter. World War II history in particular is absolutely full of myths that have just grown over time. No doubt I will have accidentally proliferated one somewhere in this video despite my best efforts. In this chapter, therefore, I'll be asking you to take different perspectives to those you may be used to. At a cursory glance, it appears to have become quite fashionable to paint the B-29 as a failure in some circles online, and the turret system sometimes gets included in this so-called failure. The main source of this position appears to be a Quora post. Yeah. The B-29 went into operation just 18 months after its first flight. It was rushed into service as it was believed to be a weapon capable of ending the war. The first B-29s to fly from the Marianas departed in October 1944. 10 months later, the war was over. Rushing the B-29s into service came with the necessary costs of sacrificing several thousand aircrew to mechanical failures, which would have normally been ironed out during a testing phase. Again, I am not here to discuss the ethics of that decision. The most common failure was due to overheating of the engines, and that would require an entire video in itself to cover in detail. The engine overheating became less of an issue as the final year of the war progressed, but was never fully solved until after the war. Following the capture of Iwo Jima, Okinawa, and improved rescue patrols from PBY Catalinas, which, by the way, one of the best-looking aircraft of World War II, the numbers of crew lost due to mechanical failures progressively fell month by month. From the perspective of Japanese citizens, these mechanical issues meant that a firebombing raid, which would normally comprise of 100 B-29s, may comprise of 95. From their view on the receiving end, the B-29 was just an absolutely ferocious weapon. Its job was to bomb Japanese cities, and by the summer of 1945, it conducted that job ruthlessly. So, from a conservative and safety-conscious engineer perspective, the B-29 could be called a failure. From an ethical perspective, well, as I keep saying, you need to answer that one yourself. But from a military perspective of end the war as quickly as possible, I think calling the B-29 a failure is disingenuous at best. You may have seen these photos of the B-29 scrapyard on Tinian. Surely a sign of an unreliable and unserviceable aircraft. Maybe, but remember, high numbers of returning bombers on the European front were scrapped due to damage on returning, or they were fixed up and sent back. With no such services on the Marianas, heavily damaged bombers would simply just be pushed into the scrap heap. No problem at all for the US. They just build more of them until the war was over. Or how about an alternative view? Remember that survivorship bias comment I made earlier? Perhaps what we're seeing here are the bombers that brought their crews back alive, where a less robust aircraft would have never made it all the way home. Without extensive historical research, I can't assign any truth to that, but it always pays to remember, getting the full story on reliability can be tricky, and without good historical sources, or misattributed sources, a Quora post is just someone's opinion. This is unrelated to any statistical arguments, but I'd also like to mention two B-29s, Pride of the Yankees and Holy Joe. Both made it all the way from Japan back to the Marianas after losing 2 engines on the same wing. Surely that has to be amongst the greatest feats of airmanship of the entire war. That is at least an 8-hour flight. One thing I am confident about, when used in the Pacific Theatre, the B-29 turret system was highly effective. Now, I could talk for hours about this, to be honest. The USAAF kept good records, but there's already a channel that's done an outstanding job of that. Keith at the World War II US Bombers channel discusses the statistics of B-29 operations in detail and provides extensive sources. So, for more info, I highly recommend you go visit his channel. But I only need 2 pieces of information probably to convince you the B-29 fire control system was effective. Both of these are taken from the most dry and boring source I could find, the US Army Air Force Statistical Digest from 1945. As for the question of how well the B-29 would perform in Europe, there are far too many confounding variables for me to speculate. So let's be clear, I'm only talking about the effectiveness of the fire control system as it was used in the Pacific Theatre of World War II. The first piece of information is the fighter-kill ratio. A total of 414 B-29s were lost in the Pacific Theatre. Of those, 74 were lost to enemy fighters. Another 19 were lost to, quote, enemy aircraft and flak, end quote. That is bombers that were seen to be hit by both. So let's be really conservative and assume all of those 19 would have made it back had they not been hit by the fighters. That's an absolute maximum of 93 B-29s lost to fighters in total. The B-29s shot down 969 enemy fighters. That is a lot. That gives a conservative kill ratio of 10.4 to 1. An unreliable and ineffective fire control system would not shoot down nearly 1,000 fighters. It seems that LeMay was correct when he said, quote, "These big boys can take care of themselves," end quote. Where they were used, the turrets protected the bombers. But they weren't always used. A common argument against the fire control system is that the B-29s only became effective bombers when the ammunition was removed to save weight and they were flown low and on night missions. That is how Tokyo was firebombed in March of 1945. A common narrative is that following the wild success of that raid, all missions were flown without the turret system. After all, the silver plate variants which dropped the atomic bombs had the turrets removed entirely. This is a gross oversimplification, and it leads to my second piece of supporting information. This plot of fighter kills by B-29s by month demonstrates that. Here's the date of that pivotal low-level Tokyo raid. Half of the fighter kills by B-29s took place after that. And to be clear, those are verified kills by B-29 gunners, not by the fighter escorts which sometimes flew from the newly captured Iwo Jima and Okinawa. Let's back that up further. Here are the numbers of aircraft flown during night and day by month. The majority of raids were still flown in daylight right until the final 6 weeks of the war. The notion that all of the turrets were just ripped out and everything was done low level and at night time after March 1945 is just not true. The truth is, there was no single doctrine for bombing. LeMay and his team were, putting it bluntly, huge data nerds. Every sortie was considered individually with tailored configurations. Some were flown at night at low altitude, some were flown during the day at high altitude, right until the end of the war. And that includes the extremely effective mining operations which were also carried out by B-29s. Many of the recommendations for formations, loadouts and turret configurations came from the work of an operations analyst named Alex Green, who, at LeMay's recommendation, was awarded the Truman Medal of Freedom. That was the highest wartime honour for a civilian. A campaign like that carried out in the Pacific is all about balancing resources. For targets where fighter opposition was unlikely, why risk the lives of 3 extra crew members if they're unlikely to be of any use? Save those resources for when they're needed, and put another 500-pound bomb in the bomb bay instead. Now, I also suspect there was another reason for not flying many of the low-altitude night missions with turrets active. Friendly fire. I couldn't find any reliable information on this, so I really want to emphasise this is just a theory. But for night missions where visibility was basically zero, it may have been determined the B-29s were more of a threat to each other than the Japanese fighters. There was even a design flaw in the turret system that lends some credence to this. If a gunner passed secondary control of a turret to another gunner who was actively firing, the released turret would immediately start firing too, and it'd continue to do so as it slewed around to match the alignment of the gunner's sight, and that'd potentially spray bullets all over a bomber formation. I do wonder if some of those 93 bombers lost to fighters were actually friendly fire incidents. The switch to low-level bombing where possible is not a testament to the fictional unreliability of the B-29 fire control system. The system was quite clearly perfectly capable of defending the bombers against Japanese fighters. It's a testament to the lack of Japanese opposition and the ineffectiveness of the Norden bomb site. Though the B-29's fire control system was undoubtedly the most advanced aerial gunnery solution applied in World War II, by the time the next major war rolled around, it was quickly obsolete. B-29s were used to great effect during the Korean War. Initially, they went largely unchallenged and were generally easily able to shoot down the small numbers of Korean fighters that attempted to intercept them. This changed as soon as the Soviets began providing MiG-15s to the North Koreans. The turret system was not designed for such high-speed jet interceptors, and B-29s were suddenly incredibly vulnerable, with many lost to enemy fire. Though one B-29 tailgunner did manage to shoot down a MiG. The US stopped flying the bombers unescorted, and they were largely retired from the front line of military service after the war. Only one comparable remote turret system was built after the B-29, and that was on the Convair B-36. Like the B-36 itself, that system was wholly unhinged by comparison. I believe I'm now legally obliged to make a video about that now that I've mentioned it. Check back here in a few months for that, I guess. In fact, while we're talking about that, I am desperately looking for technical documents about the B-36 fire control system. If you have any or know where I can find them, feel free to email me. Some B-29s remained in service for the military to be used for recon, rescue, and electronics warfare. However, the B-29 did have a rather varied and interesting legacy. The Soviets cloned it from a couple that were forced to make emergency landings in Soviet territory at the end of World War II. The result was the Tu-4. No reliable word on how effective it was, though apparently they replaced all the 50 cal guns with 23mm cannons. I'd be surprised if they were able to make an effective copy of the fire control system, though. Back in the US, B-29s were used as a testbed for the Goblin parasite fighter, possibly one of the wackiest configurations ever flown. Some were privately purchased and converted into mobile TV transmitters for the Stratavision company. Doc and Fifi are the only two still flying today. They're maintained as commemorative aircraft, and I have nothing but respect for the crews that keep these beautiful aircraft flying. And that takes me back to the quote from the start of this video. You could say I took it a little out of context. Caprione's character in the movie preceded it with these words, quote, "Airplanes are not tools for war. They're not for making money." End quote. With 100 years of hindsight, that sounds incredibly naive. But here's a final bombshell. There is technically a third very, very heavily modified B-29 still flying if you're willing to get loose with definitions. And in some ways, it meets Miyazaki's version of Caprione's requirements for an airplane. Many of its flights are not to make money. And they're not for war. In fact, it still flies regularly, and not as a showpiece. It's in genuine service. It may be my single favourite aircraft on Earth right now. Can you guess what it is? It's the Super Guppy. After World War II, Boeing enlarged the fuselage of the B-29 to create the C-97. They further modified that to create a passenger variant, the Boeing 377. And in the 1960s, several 377s were again modified to create the Super Guppies. Only one still flies today, and it's owned by NASA, who have no plans to retire it anytime soon. Only the cockpit, wings, tail, control system, front landing gear, and a few other bits and pieces share commonality with the B-29, but once you see the resemblance, you can't unsee it. And yes, it flies contracts for the military every now and then, but NASA's Super Guppy has carried countless parts around the US to further the exploration of space. And that is a mission I am most certainly happy to celebrate. Thank you very much for watching.